In this lesson, we're going to finally put together the idea of counting with probability to talk about calculated probabilities. While this section seems a little bit short in the number of slides, each of these examples has a very meaningful application that you should pay careful attention to the techniques so that you can do it in other types of problems. For our first example, suppose that there are 6 men and 3 women in the company. Recently, one man was promoted to be the manager, and another man was promoted to be the assistant manager. We want to know, was this gender bias? Now keep in mind there are twice as many men as women in the company. We don't really know very well just from looking at it. Maybe? Hard to say. There are more men than women, but they were both men that were promoted. So what we're going to do is figure out the probability that among those 9 employees, the random choice of 2 would give you both men. I should also point out that the order matters here because it matters who was promoted to manager and who was promoted to assistant manager. Let's take a look at how this works. In order to do a meaningful probability, we're going to let the sample be all possible choices of manager and assistant manager among all 9 employees. And we want to know the probability that among all of these choices, they came from the men. That's going to be our event. Now that we have this in place, we're going to use our counting techniques to try to figure out the sizes of both the E and the S. For the size of S, you have 2 promotions. You have a manager and an assistant manager. Well, there's 9 choices for the manager from all employees, and after the manager is chosen, you wouldn't choose the same person to be the assistant manager, so we only have 8 choices for the assistant manager. That comes out to 72. Now for E, we're making the assumption that they are men among the random choices. So there's 6 choices for the manager and 5 choices for the assistant manager. Now let's calculate the probability. Remember, the probability formula is the size of the event over the size of the sample. And that's all my notation for the N of E and N of S is just how big they are. We get 30 divided by 72. Let's write this one as a percent this time. I get about 41.67%. Now that percentage is kind of high, but it's not that high. So it's kind of hard to say. If that number were something like 5%, that the probability of randomly choosing and it both being men was 5%, yeah, I would definitely say gender bias. 10 to 20%, I might say maybe. But at 41%, that's nearly a coin flip. So I'm going to say, I don't think it was gender bias, but you might look at more evidence to support the claim. Overall, I'll say this is probably not gender bias. Next example. Suppose a certain passkey consists of 2 letters followed by 2 digits. Assuming the choice of passkey is equally likely, what is the probability that a passkey has some letter or some digit repeated? The technique in this one is going to be a little bit tricky. First off, the size of S. S is going to be any passkey whatsoever. You've got 2 letters followed by 2 digits. Nothing to do with repeats, just 2 letters followed by 2 digits. You've got 26 choices for each of your 2 letters and 10 choices for each of your 2 digits. This gives you 67,600 possible passkeys. Now for N of E, I'm going to break it down a little bit. The word OR is a little bit tricky here. Here's the 3 cases that I'll consider. If it has some letter or some digit repeated, then you could have a letter repeated but not a digit. You could have a digit repeated but not a letter. And then often when the word OR is used, it's not necessarily the exclusive OR. It could be that both are repeated. And that's what we will assume here. A letter repeated but not a digit. For your first letter, you have 26 choices. But now this is the tricky one. How many choices do you have for the next letter? You might say 26 because we're talking about repeats. But think about it for a second. Let's say my first letter was an L. What would my second letter have to be if there were a repeat? It would be an L. How many choices did I have to choose that second L? One. One choice. I didn't get a choice. My second letter has to be the same as my first letter. So in the context of a forced repeat, there's only one choice. Now let's go to the digits. We're assuming the digits do not repeat, so that's 10 choices for the first and 9 for the second. Next one, digit repeated but not a letter. Digit repeated, you'd have 10 choices for the first digit and 1 for the second. Forced repeat. And then for the letter, you'd have 26 and 25. Finally, for both repeated, 26 choices for the first letter, 1 for the second, it's a repeat. 10 choices for the first digit, 1 for the repeat. Now let's multiply all of these together. Here's the answers I get from these three. And then finally, just to get the actual value of the event size, we will add these three numbers together. For this, I get 9,100 possible passkeys. Now let's take a look for a second. Had you done this wrong, you might have this number being too big. A little check is that notice the event size is smaller than the sample size. Now let's just calculate our probability. We'll write it as a percentage. The probability of E would be 9,100 divided by 67,600. Remember, it's just the E over S. If I convert that to a percentage, I get about 13.5%. So not a lot of these passkeys are going to have a repeat letter or digit. Let me mention one other way of expressing your answer. While the answer that I just gave is great, and it's probably the better choice of answer, when you start getting into very small probabilities, like the Powerball example from my previous lesson, notice that they had given their probabilities as 1 out of blank. It would be nice to get 1 out of something as well. The way to do that is you would say 1 out of, and then the number that you would get would actually be given by the other direction. 67,600 divided by 9,100. And you could round that to about 7.43 as another option for the probability. So take your pick. And I will tell you, if this number is less than 1%, it's probably a good idea to use this method instead in order to write down your answer. Remember to use that method, simply flip the roll of E and S and say 1 out of that number. Next example. 8 laborers arrive at a construction site seeking work. If each laborer is equally likely to be given work or sent home, what is the probability that at least 2 laborers will be given work? This one's a little bit strange. So in order to count the ways that you'll have at least 2 people on there, what's actually more useful is to go in reverse. Think about what we'd have to do to find this. We'd have to figure out how many ways you could get 2 people on the job site out of the 8. And by the way, what I mean there is which 2? Which 2 people would be on the job site of the 8? And then it says at least 2, so then we'd have to do 3, 4, 5, 6, 7, and 8. That is a lot of work. So let me bring it up in a different avenue. To get started, let's look at the sample size. The sample size has 8 laborers, and each person is going to walk up to the person in charge, and the person in charge is going to tell them whether they're given work or sent home. It's equally likely, so you have 2 choices: get work or go home. You can even imagine this as he flips a coin in front of them and tells them whether they're going to get work or go home. Kind of strange, but that's what's going on in this problem. And the rest of the laborers are exactly the same thing. There are 2 choices for each one. So with that, we end up with 256 possibilities. And these are the ways that we could have people on the job site. It also takes into account who is on the job site as well. Now let me talk about opposites for a minute. The opposite event is sometimes known as a complement. Basically, whenever you see that you've got all these cases of 2, 3, 4, 5, 6, 7, 8, it's easier to just say, well, let's look at the opposite of no more than 1. If no more than 1 is given work, that's the opposite case. If we could count that, we could subtract it from the 256 to find out what we're doing for at least 2. So now let's break that up into 2 pieces. For 0 laborers, that's actually one of the things that's not at least 2. It could be that everybody is sent home. How many ways can that be done? Well, if you think about it with the coin flip, it makes sense. Think about it as heads, you stay, tails, you go home. If you get tails on every single coin flip, everybody goes home, and there's only one possibility for that to occur. You'd basically have to flip tails every time. Now, how about 1 laborer? 1 laborer is more so the question of who is on the job site. Remember, 8 showed up seeking work, but only 1 got work. Well, that is going to leave us with 8 possibilities. It's not a question of how many are there, but who is there. There are 8 different ways to have 1 person. It's the person who's there. So when we put that together, we see that our opposite event is 9 possibilities. So from there, we can finally calculate n of e. The event is at least 2 people are there. We found out that if the event doesn't occur, there are 9 possibilities, and there were 256 total. So if I do 256 minus 9, I get 247, and that is the number of possibilities when we're talking about at least 2. We can now calculate the probability. The probability would be 247 out of 256, and I'll write that as a percentage, to get a 96.48% chance of having at least 2 people on the job site. In the other way of writing it, if we want to do 1 out of, remember for 1 out of, we'll flip the fraction and do 256 over 247 instead. If I do that, I get 1 out of 1.04. So as you can see, when the percentage is high like this is probably more meaningful than the 1 out of answer. Again, I would probably give a percentage unless it turns into being less than 1%. At less than 1%, I would definitely say 1 out of whatever number you get. Last example. A home security system uses a 4-digit code. What is the probability that the code will include exactly 15 and exactly 17? There's going to be some sort of thought process similar to what we did in the last example here. However, the sample is easy enough. The sample is going to be all the 4-digit codes, so you've got 4 blanks, and then there's no requirement on repeats or anything. It could be any of the code with all 10s, and you get 10,000 possible codes for this system. But we're wanting to look at the event that there's exactly 15 and exactly 17. Now, unfortunately, I cannot draw blanks here because there's some funny things going on, but I'll tell you how it works. If the code has 15 and 17, imagine for a second a sample code. I usually use this notation whenever I write a sample. There's no indication of multiplication, it's just an idea. If it has a 5 in it, you can look at your possibilities right now. How many choices do you have for the position of the 5? You could put it here, or here, or here, or here. There are 4 possibilities, and I'm going to label that. I'm going to choose to put the 5 in the 3rd blank, just for fun. It doesn't really matter where, but we did have 4 possibilities. Now it also has to have exactly 17. So now look at your example. How many choices do you have for the position of the 7? 3 choices. I'll put the 7 in the 2nd slot, just to do it there. Now I don't have a full code yet, I've only got 2 digits in here. So then to finish it, I need to fill in whatever the other 2 slots are. In my case, it's the 1st and the 4th slot, but it could be any of the 2 slots, and I'll just fill them in. How many choices do I have for the digits remaining in here? If you said 10, you're a little off, because I cannot use 7 or 5 again. So I actually have 8 choices. 8 being all the numbers besides 7 and 5. So I could pick any number I want. How about 1? Now the 1 could be repeated if I wanted to. So since repeats are allowed, there's another choice for the 8 here. Just for the sake of including the repeat, I'll put a 1 here as well. If I multiply that together, I get 768 codes. We'll have this particular scheme of 17 and 15. Now let's do the probability. Again, the probability is the number of elements in E divided by the number of elements in S, and if I do that, I get 7.68%. If I do it the other way, you could also do 1 out of, and remember just to flip it the other way. 10,000 divided by 768 would be about 13.02 for that way of looking at the probability. So out of about every 13 codes, you would expect a code to have exactly 15 and exactly 17.